Mr. Professor Scardesini is full professor of building physics at the Swiss Federal University of Technology in Lausanne, and also head of the solar energy and building physics in the laboratory
of the Swiss Federal Institute of Technology.
Okay. And also energy efficiency in the built environment since 1994. Sorry for
that's okay. Thank you for
some
this.
Problems.
Thank you for this kind introduction. Kalimera, I should say Kalispera, because we go gently to the end of the day. And we have the task this afternoon to entertain you with some presentation. This is nap time after snack, so I know it's difficult for you. And hopefully I will try to maintain the audience. I'm sure I will maintain you alive and interested by what we present this afternoon. I will entertain you about green lighting, which is a short way. It's a short way to express high performance integrated daylighting and electric lighting systems. And by sure we prefer green lighting, it's shorter. This is a part of the activity of our lab. Actually, our lab, the Solar Energy and Building Physics Lab, with about 40 to 50 people actually, is dealing with 6 different research axes: urban physics, which is going maybe presented by Darren Robinson, who just left us to go back to his home country, UK, nanotechnology for solar and solar integration and HVAC control, different field that I will not mention this afternoon by trying to stick on green lighting. Let's begin with an overture. This is usually what we do, or what some music writers do in the opera and in the symphony. I'll try to do the best I can. I will begin with this picture. This is the picture of a rather banal, is probably exaggerated building. In fact, it's an historical building which were built in the second half of the 19th century. He is protected. And the things that you maybe don't see on the picture, and that's the reason why I'm beginning at purpose with this building, which has been refurbished in 2010, is that it's an Energy Plus building. We heard this morning that's Minergie standard. I will say some word about Minergie. I'm moving to a new label, which is called Minergie A, for zero energy building and Energy Plus building. And I will use this building to show you where we are regarding heating and cooling, and to show you where we have to go regarding the electricity consumption of building. This is, for sure, there is a lot of things to do regarding this point. But this building built in Basel, actually we did not work on the design, we work on the assessment of the solar utilization potential of this district of about 30 to 40,000 inhabitants, one of the densest district that we have in our country. Refurbished in 2010, and as you can see, this is maybe an example. One of the first we have in the country that you can achieve very high standard for energy consumption, going even better than zero, with a building which is protected, which is by law protected, and this was done in this case. Within my talk, I will use this building, the net zero energy building, new construction, not only refurbished building. I will use an example from our colleague from the Swiss Federal Institute of Technology in Zurich, actually the sister ship in Zurich, as we are actually in Lausanne. There are 2 this kind of institute in our country, which are ruled by the Swiss Federal Institution, or the Swiss Federal Council, actually, for this type of technical university. I will also use our own solar experimental building in Lausanne that we built in 1982 and refurbished in 1999 to show you that some of the focus that have been presented this morning, the zero energy building, the electricity demand within building which is growing, has been already spotted something like 15 years ago in our building, and that we have moved in some direction to set up integrated lighting system that's maybe not go to 0 watt per square meter as light power density, but at least can go very close to 0, and this will be the center of my talk. I will also use some example for Singapore. We work with the National University of Singapore to set up a zero energy building in a climate which is like the Greek climate, which is a cooling load dominated climate, as you know, Switzerland is a heating load-dominated climate, but I would like also to show with this example that we can do the same for a cooling load-dominated climate. And then finally, hopefully conclude in 30 minutes. So let's, and that was very nice that the former presentation began with this 2000 Watt Society program. I will not go into too many details of this program, but it's just to remember that we are facing tremendous problem, tremendous challenges in front of us regarding climate changing, mitigation of climate changes, depletion of resources, and actually the way that the Swiss federal government reacted, this was about 8 years ago already, is to promote the 2000 Watt Society program. As mentioned before, in Switzerland actually we are using as primary energy 6,500 watts per capita, per person, if we assume that the energy is used 24/7, all the day long, all the year long, and this is the average of power, including the imported energy, and actually consumed on-site in the country, it's about 5,000 watts on average, 24/7 per capita per person. We have to go down to 2,000. 2,000 is today the average of the world average. There are countries like Bangladesh using 200 watt per capita. There are countries like Switzerland using 6,500, United States using 12,000 watts per capita actually, and this makes for you the picture of the challenge we have in front of us. What does it mean in a concrete way? You see the red bars, which represent the family today for housing, living, habitat, eating, the mobility, and so on. And the green figure represents the family of 2050, maybe 2080, that has to use something like 3 to 4 times less energy, and especially to heat building. To make the principle maybe a little more clear, this was mentioned this morning, we have, I think, all over the world to aim at car. This is not exactly the performance of this car, but we have to aim to cars consuming not more than 3 liters of gas per 100 kilometers. Most of them are using 10 to 15, if not 25 in some cases. We have to go down to 3 for all the cars on average. And we have to do the same for building. Actually, it's more Minergie P, you have seen this morning, but Minergie or Minergie P, to be very accurate, is aiming a target of 3 liters of domestic fuel per square meter per year to heat a building in our climate or to cool a building in your climate. This figure of 3 liters will come again in my talk, and this is probably another way to understand the 2000 Watt Society. This is where we have to go. And this morning you have seen also a picture of Mr. Bayele showing the situation of a canton. This is not the canton of Vaud, this is the canton of my original city, Zurich, actually, even if my name doesn't tell it. And these are the figures for the canton of Zurich. And actually, as said this morning, the big difficulty are the existing building, renovation of building. But I've shown an example that even for an historical building, we can go down to very low figure, even making an energy plus building with very 100 or 150 years old building. But still, you can see the consumption for heating of the building. Before 75, this was very high. And we have to go down, in fact, we have to go down to this figure of 100 megajoule per square meter per year, which correspond to 3 liters of domestic oil per square meter per year. Sorry, I'm a physicist. That's the reason I'm using these units. Nobody is perfect. But again, you will see this figure of 100 at the target. To balance some building that will remain rather high, even if refurbish them, we have to go down with other building probably to nil, to balance the weights of the old ancient building, because we hopefully, or we certainly cannot bring all the Swiss building to net zero energy building in a reasonable time. So to reach this target underneath the 3 liter or 100 megajoule per square meter per year target, which is the 2000 Watt Society target, is where we have to go. And I will show you some example, and I will show you the problem that actually we have spotted from this experience. Let's take an example of a new building. This is a building which we didn't build in Lausanne. We would have liked to do it. It was built close to Zurich by our sister ship, the Swiss Federal Institute of Technology in Zurich, the ETH Zurich. And actually, it's a brand new building. It was built in 2007, 2008. I have no time, opportunity to go into detail. It's a rather nice building, but as you can see from the figure, it has a high level of thermal insulation, up to 30 centimeters, even more glass wool, triple E-coated glazing, so rather advanced technology with a U value of 0.4 watts per square meter per K, if you know this figure. Daylighting technology, this is something on which I will focus a little bit. Free cooling to avoid any HVAC system, as we have here, by using the ground to preheat the air in winter and pre-cool the air in summer. And other technology like PV, solar thermal, and even rainwater recovery and biological toilet, which is actually gently becoming a new challenge for us in many countries, but I don't have the time to go in this in more explanation this afternoon. Let's see just some picture. This is actually a picture of the atrium of this building, in which the researcher of the Federal Material Testing Institute and the Water Research Institute are actually working in. You can see the atrium with the daylight source at the top. You can see the office room here. And this is the view of an office room with a single electric lighting system in. So that means that most of the lighting for session, meeting, discussion, and others, most of the lighting is due to daylight, actually. And probably this is 80% daylight provision room. That means very high efficiency regarding the use of daylight. This is the view of the Canadian well, which is a way of using the ground to pre-cool the air in summer or preheat in winter. And actually, by using this way, there is no air conditioning system, classical one with compressors. Every cooling is actually made through this cooling device, which is a rather old technology, which is gently spreading, I think, all over Europe. Again, Switzerland is not cooling load dominated, but also due to the climate changes, we have the feeling that the cooling load will get larger and larger over the time, and we already sense it. Let's look to some figure compared to the 2,000 watt targets. I know there are some experts here, we can discuss some figures, but I don't have the time to go in all the details. The things which is visible is the quasi-zero, the net zero energy needs of this Forum Griesbach building, the net zero energy building I presented for heating and cooling. It's close to zero. That means there is no heating system, no cooling system beside passive solar and the Canadian well we saw. You see the targets that we have to reach. Actually, it's Minergie P, Minergie Plus. You have the explanation this morning. 3 liter for heating, close to 100 megajoule per square meter per year for heating and cooling. And you see the rest. And this is the item on which I would like you to concentrate the needs and consumption and demand for electricity, lighting, electrical appliances, plug loads, computer, IT, and the embodied energy. And this morning we had a beautiful talk on embodied energy. So this is obvious. As the rest is going close to, as the heating load is going to, or cooling load is going close to zero, the other energy pits, which is actually the electricity demand and embodied energy, becomes dominant. So what can we do, at least, to reduce these two things? We had the chance, this is already 15 years ago, if even more, I think it's 25, I'm realizing that I'm gently getting old. Now, something about 20 years ago, we started already a daylighting research program, which was rather advanced, with sure a lot of support from the state, a lot of money, and a lot of people, PhDs, and work with architects, physicists, and engineers. And actually, one of the response to reduce this electricity need is the use of daylighting. And actually, let's say we design a new type of advanced daylighting system, which are using non-imaging optics. Again, I don't have the time to explain what non-imaging means. It means that we use a kind of optics which is not used for glasses, telescope, camera, videos, but it's used by physicists to capture a daylight flux or an electric light flux with the maximum efficiency. And it has, on the theory, 100% efficiency without breaking any of the thermodynamics principles, but don't have the time to go into details. In fact, actually, non-imaging, we named this technology using ancient Greek name, anidolic, eidolon, non-image. And this anidolic optics or optical devices, this is a 1-to-1 scale office, is able to multiply by a factor 2 to 3 the amount of daylight on a desk 8 meters away from the facade. And you will see an example from Singapore where we brought this light 12 to 14 meters deep into the office. Even if it's a side lighting system, we bring it in using this very powerful advanced technology. And again, there is a lot of books on non-imaging optics. Some of them are very famous in case you want to understand how it works. And there is proof and beautiful theorem, beautiful proofs on how it works, an equation for people who like equation like I do. And this is an example of the same office without the system, again 8 meters away from the facade, 3 times more lighting, 80% energy saving compared to this office, where probably at least the end of the office will depend most of the time from electric lighting. We also set up an advanced daylighting research program. I don't have the time to go into details. I will give you the internet address if you are interested by. Developing hardware tools, software tools, hardware with simulators, artificial skies, science simulator, goniophotometers, and movable and one-to-one scale test module in which we could test different type of daylighting system from the industry, from the university side, and have a real measurement of the energy saving, the visual comfort, the visual performances, the amenity, and even the impact of light on the photobiological aspect of human being, the so-called circadian rhythm, the rhythm that brings us to sleep or to be awake in the morning and to go to sleep in the evening, and hopefully not in the afternoon. And software. Again, a lot of software development, and I will be delighted to give you some more explanation if you are interested later on. So daylighting was a focus, it's still focus, and we had the chance to implement this advanced anidolic daylighting system through the help of Dimitri Papadaniel and his 2 former architect colleagues. He was the one that helped us to refurbish the building in 1999. The building was built in 1982 by the same architecture team and was refurbished in 1999. And when we refurbished it, we integrated on all the 3 floors of this 1,000 square meter building, we integrated this advanced daylighting system. We also, in order to bring the office room almost to independence from the electric light. We are not so close, but I think we are close to 85–90% daylighting provision for the office room. We also use larch, which is a local type of wood. There is no protection paint. There is accepting these light shelves which are protecting the facade against water, which is brought by Thunderstorm, for example. And we also implemented new glazing. In those time, double insulated glass with e-coating. Today, it would be triple insulated glass with e-coating. All over, we took the opportunity to try to reduce the embodied energy and try to reduce the electricity demand of this building in 1999. Underneath the figure you already have, and already in those times it's still the most performance building of the EPFL campus, which is very large, and actually since 82, since more than 30 years. Let's look to the figures, and you can see on these figures that we go regarding heating underneath the 100 megajoule figure. It's a 2 liter per square meter per year building for heating, so we are underneath. We are better than the 2,000 watts target, but there is a electricity need for lighting and appliances. Today, despite the use of daylighting system, this is still high. But I will show you that in some of our offices, we went close to zero for electric lighting needs by developing very advanced electric lighting system. The building is also relying 60% on solar, passive solar, and as seen here, there is a small PV, building integrated PV system, which is covering half of the electricity need, despite of what the drawing is actually telling. If you go to the figure again, the building, this is actually the Minagi P figure, compared to the building standard. To be very honest, this is the building standard before 2008. Actually, the so-called SIA building standard is very close to Minagi, as presented this morning, but still, our building is very close to Minagi P, is underneath the 100 megajoule for heating, and still electricity need, embodied energy still remain. How can we reduce further the use of electricity for lighting? This is what I would like to show you in the end of my talk. First of all, you have a view of the office room, and you see for a sunny day, for a cloudy day, the light flux coming from the anidolic, this advanced daylighting system, which is actually on the upper part of the facade, and you see here the light shelf, which is made of wood, protecting against the sun. It's a sun shading device, mobile, never get trouble, fixed, never get trouble as a mobile system. We do have two blinds, external blinds in case we really need to block the sun, and you see the same view here for diffuser radiation. This is actually the type of lampadaire or standing luminaries that we use close to task lighting devices with CFL, compact fluorescent lamp, and infrared sensor, presence sensor, in order to switch them off when there is nobody in the room. This is actually what we had in the room, in the office room. It's a rather standard equipment in the room. And these are the results. Actually, the average for lighting, the so-called lighting power density of this room or of the building is actually equal to 9 watts per square meter. It's a little bit better than what we have in our, usually in Switzerland, in between 10 to 12. There are buildings where you can find figure up to 25 or 15. But actually this is the average, and you see that we have the chance to test, monitor it with users, with people here, and to test up to 15 different offices. And you see that some are worse or have poorest figure than 9, but some have better figure than 9, and I will explain you why. It's sort of simple. First one, today I think there is not much to say about it because incandescent light bulbs are banned anyway, but in those times, this was done in 2009, some of these lamps were still existing. So most of the extra electricity consumption of this office, again, every number here is an office. I would not tell you where my office is actually. It's maybe this one. No, I'm kidding. But this is our offices, and you see that when you have task lighting with incandescent lamp, for sure, incandescent lamp are not efficient at all. This brings high figure. If you ban the incandescent lights, and if you have a high fraction of indirect type of lighting with this lampadaire, that task luminaries that you have seen before. For the reason that you have indirect type of lighting, you have a rather inefficient type of lighting, at least for energy efficiency, and so you have figure very close to 9. Sorry for that. And if you go close to and if you use direct type of lighting, oversized or direct side of lighting, which is optimal, then you go down to figure close to 4. And we have even done better because we went down to figure of 3 watts per square meter of light power density instead of 9 on average. How is it? Easy. First of all, avoid using poor lighting sources with low lighting efficacy, like incandescent bulb and some of the CFL. Not all of them are very good. Even LED, I will say some word on white LED in a moment. Use a lot of daylight because daylight has a luminous efficacy higher than 100 lumen per watt. And even LED, white LED today, cannot reach this figure. And just remember that incandescent light bulbs have luminous efficacy of about 10 to 15 lumen per watt. And that's the reason why we banned them. So the use of daylight combined with very efficient light sources and very efficient luminaries. Let's see an example. This is actually a luminary which has an optical efficiency of 96%. We measure it, 96%, again, because it's based on non-imaging optics. It's a product of the market. I'm in an ASHRAE conference, so I'm not allowed to say who is selling it on the market. It's a Swiss company. But actually, 96% optical efficiency is probably one of the highest we have never seen. The very good luminaire we had in the offices, the one you saw very quickly, they have optical efficiency of 69%, which is still high, but 96 is the reason why we could go down to 3.5 watt per square meter lighting power and density in 1 or 2 office rooms. This is not the only reason. The use of this non-imaging advanced daylighting system and the use of the optimal size and optimal position of direct type of lighting and avoiding to have extra useless luminaries on the ceiling. You may say, or you may ask, why not using LED? Actually, this is what we try to do. And as said, this was done in 2009. There is a thesis from Friedrich Lienert, in case you're interested by the result. We also tried not only LED, white LED, but we tried many lighting sources. And I would like just to focus a little bit on these two sources. This is actually the long, rather efficient fluorescent tube with a 16 millimeter diameter that can go up to luminous efficacy will go close to 190 lumen per watt. This was measured in this 1.5 meter Ulbricht sphere. And actually, 4 years ago, the white LED you could find on the market, not in the lab where you can find extra very efficient LED that can probably not withstand more than 1,000 hours of lifetime. This normal, on the market available white LED had a luminous efficacy of about 30, a little bit more than 30, but underneath 40 lumen per watt. Today, the expectation is probably that the LED, they go higher and they go very quick. So I'm expecting today to have on the market that everybody, you and us, could purchase LED, white LED, with an efficacy of 60 lumen per watt. But the prognostic, what was planned for this LED is to reach already 80 today, and we see that they are not reaching this figure on the day-to-day life so quick. But still here, we did a simulation where this kind of white LED and a luminaire actually designed by an Italian company, which you can find on the market, and assuming a luminous efficacy of 80, remember what we had was underneath 40, but assuming that within 2, 3, or 5 years on the market, we will find at a reasonable price LED, white LED, with an efficacy of 80 lumen per watt. In this case, we could go down to a figure of light power density very close to 3 watt per square meter. And if the LED go up to 100 and 120, as we expect maybe for 2020, this figure could go underneath 3, maybe 2.5 watt per square meter, whereas it's true, an illuminance in this case, which is slightly underneath the 300 lux work plane illuminance, but remember, this is a complement of daylight, and even if we have people working during night, the complement in the morning and the evening is certainly enough to complement a very efficient daylighting system. During the nighttime, our students would probably use a task lighting using LED, as you can find today, very efficient white LED with task lighting. To conclude, this is the summary of what you have to do to go down from 9 watt per square meter down to 3. First of all, use compact fluorescent lamp, then use the direct lighting mode, even if the preference of people is for indirect lighting, at least in our country. Have an optimal design of these direct modes of lighting and very efficient light sources, luminaries, combined with the use of daylighting. And altogether, this brings the figure, at least this is what we have measured in one of 2 offices, the figure down to 3 watt per square meter. And hopefully we will be able to spread this lighting system in all the offices, and I will be able to show you higher performances for electricity consumption of the building in a couple of years. Just to show you that you can do the same or achieve similar results for cooling load-dominated climates, I will just show you some slide on the building which is in Singapore. It's actually a refurbishment of the building. The building is owned by the Building Construction Authorities of Singapore, and we had the chance to work with Stefan Wittkopf, who was professor at the National University of Singapore. The collaboration was so fine that he moved to Lucerne in Switzerland. Actually, he's professor in Lucerne, but in those times, this was only 2 years ago, we had the chance to work on the design of the lighting system of this rather advanced net zero energy building for Singapore, which is one of the first in Asia. Probably there is another one in Malaysia, but this is probably one of the first. Daylighting system, I would like to say some word on the PV system, which is supplying electricity to the air conditioning system. This is cooling load dominated climates, and the lighting system that you can see on the facade here, that you probably can better understand by seeing here this picture of the anhydraulic system with an anhydraulic ceiling bringing the light in 12 meters away from the facade, combined with a vertical lighting system. This is core daylighting, this is side daylighting, and altogether this is electrochromic glazing, but altogether And you can see the figure here. This has to be also complemented by the PV solar electricity produced by the building, combining this advanced daylighting technology and the rather modest insulation of the facade. In Singapore, the building standard and the building code were not so strict. And actually, if you see here, it's about 10 to 15 centimeter of glass wool and double insulated glazing on the facade, which is not so advanced, at least if we compare to the standard we have in Switzerland and in other countries. But still, if we look to the figures, this is the vertical lighting system from the core daylighting system with it's a product on the market actually, and this is the side lighting system. All the two luminary you see here, this is actually a daylight luminary, this is a daylight luminary, and you see we have been very careful to switch off the electric lighting system. You see the electric lighting luminary here, they are off. If we look to the figure, and this will be my last slide, you can see the energy demand, which is in red bars here for all the months of the year 2010, and you can see here the electricity production by the 1,000 square meter PV production. It's more than a net zero. Actually, it's an energy plus building. Only electricity for heat, for cooling, lighting through an air conditioning system, which is a rather good EER, a good COP, but still an energy efficiency in lighting and the thermal insulation. This is time to conclude. I hope that you are convinced by some of the sentences which are there. First of all, that we can reduce for heating and cooling, we can reduce the primary energy demand for heating and cooling down to zero or close to zero. And you have seen some example even this morning from Mr. Bayeler through green building technology. It has a cost, but the cost will certainly go down also very fast as soon as we produce or we construct more of this building. The primary energy demand for lighting and electrical appliances, the plug loads, still remain high. And this is where we have today, I think, to make the real effort of R&D, lighting and plug loads, as this was also mentioned by the previous presentation. We can go down to 3.5 watt per square meter for using green lighting technology as lighting power density figures by combining efficient electric lighting sources, efficient luminaries that you can find today on the market, and efficient daylighting technology. And all over this make the green lighting. And still, it remains that plug loads, computers, cafe machines, and other television screen and others that you may also find in office places, this is the real focus on which we should. Probably smart grid technology will help us to switch the things and the parasitic consumption of these devices off. And embodied energy. And we have tried by using local materials, which is wood material, to reduce the embodied energy. In case you're interested not only by Lausanne by night, but to have more information on this work, the theses are available on the leso.epfl.ch website. And to conclude, as long as we would not have windows using organic LED technology, the same technology that we use on the iPhone today already, as long as we would not have the windows using OLED to lit the building during day, to lit the building during night, the only energy saving measure would be to switch off the light. Thank you for your attention. Ευχαριστώ.
Να δώσουμε το μικρόφωνο για μία ερώτηση εδώ.
Yes, thank you very much for your presentation.
Welcome.
I would like to ask again, could you explain us this example in Singapore? There were these shading devices, I think with PV cells on top, and they were also, you said, acting as anidolic. How would that function? The light came through the PV cells, or?
So the target of this project was to reach net zero energy building in the country of Singapore, and to tell the truth, to reach it before other countries like Malaysia, China, maybe India. There are similar projects going on in this country, and the mean that we used by our colleague, we had collaboration with the architect here, which was a rather old Chinese architect, was to first of all improve the energy efficiency of the envelope, which had a very poor, no insulation at all, single glazing. So this was the first step, an easy step. Then combine, I should not say that, but all the possible daylighting system. One is the core daylighting system. It's a tube. It's actually a product which is called Solar Tube, and which is bringing light in for the top office, and then using non-imaging devices, using an anidolic daylighting system to collect the diffuse daylight, because Singapore has a very cloudy dominated climate, cloudy, warm and humid, and bring the light in through what we call an anidolic sailing. It's a light guide. In fact, there is a plenum of about 40 to 50 centimeters with reflective material, rather cheap, that you can buy easily also in the market, to bring the light in. And there is a non-imaging device. Today, we have a lot of luminaries using non-imaging devices for headlight of cars, even in building. And this was a non-imaging device to bring daylight in from the sailing down on the desk, and this was done for all the offices excepting the last office. And the cooling was provided by a rather efficient but nothing exceptional HVAC system with a rather high coefficient of performance, EER, and again the electricity which is injected in the grid, but the overall electricity production by the solar panel, 1,000 square meter of PV on the roof, were producing more energy than the electricity demand of the building. And that's it. It's where the most impressive for us was to see that it was not more than in 6 months they refurbished the building by working in an unbelievable quick, fast, and speedy way, and the target was reached already in 2010, and the first year, 2011, was already there. This was the goal of the government. So that's it. But in case you're interested, there are publications, most of them, the main author is Stefan Wittkopf. He is a German architect who spent about 10 years in Singapore and just moved to the University of Applied Sciences of Lucerne 3 months ago. Wittkopf.
All'Iratisi.
First of all, thank you for your presentation. I would like to ask you if there's a research relating the gains in daylight with the gains in daylight with the thermal gains.
It's a good point. It's a good point, and for sure this was an important point in Singapore. We made, through the first phases we did, I think in '96 on this daylighting system, we made also the analysis of the passive gain which are coming through the device itself. And sure, this is not negligible. So that's the reason why these kind of devices, they have to have an external movable textile, I think it's more easy, movable shading devices to protect them when you are in full summertime, or when even in Switzerland after the months of May or June you need to reduce the solar gain in very efficient building to avoid overheating. The advantage of non-imaging optics, again, it's a fabulous field actually, coming from high energy physics, invented in Chicago and used also at the CERN, is that you can collect daylight from all the directions. You can design your system to collect the light from a given direction, and that means that the system is optimal for diffuse daylight. He is collecting diffuse daylight in a way that you cannot reach using conventional plane or parabolic system, which should be compound parabolic system, but conventional parabolic system cannot do. So when you have a blind on it, and if there is sunshine, the blind is very light, and the light of the blind is collected. and in a certain way, most of the heat remain outside. But for sure, this type of system here or in Singapore or even in Lausanne, they have to be built with an external shading device.
I see. And one more question. I'm not familiar with this anidolic technology. Is there a comparison among the anidolic technology with, I don't know, phase change materials or electrochromic, photochromic films?
You mean comparison of efficiency or?
Yes, of efficiency.
The things we know from physics and from the measurement we did is it's by far, because the physics is behind it, the most efficient we know. And this is definitely true, first of all, because we compared by measuring devices like prismatic devices from American, German company, from Australia, laser cut panel, which have been produced there, diffuse material there are many products on the market which probably will be useful for retrofitting of building. But regarding the efficiency, if you look to the efficiency of the system to bring light deep into an office, we have not found, to be honest, any system which is more efficient. It has drawback. The drawback is probably the cost, because you have to play on the facade, and Dimitri Papadaniel could say some word on it. These were the first prototype anyway, so it costs always more. But it has some cost because it's a large system. Not the material themselves. The material themselves, they cost less than 50 euro per square meter. The reflective material is very cheap. But the fact of touching a facade, which usually is vertical, this has a cost. So we try to reduce the shape. And actually, the efficiency is not so high, but there is a product which is called Light Louver, which is a product based on non-imaging optics, and in fact it's a blind which has the same technology and is trying to reduce the size and the cost and make the implementation more easy by retrofitting a building. You should only apply the system on the external side of the facade. But the overall efficiency from the physics is lower because there is some shadowing effect. But I think the balance, cost and efficiency, is probably better for these kind of light louvers than the system we have. But the overall efficiency is definitely the best. There is even a lighting designer from Austria that have implemented this type of device at the airport of Singapore. The new Changi Airport 3 has these devices, and it's a huge hall. There are thousands of this system, which are 1 or 2 meters long and 1 meter thick, which are installed on the top of the roof to lit the whole of the airport. So again, it has a cost, but regarding the efficiency, no doubt it works.
Okay, thank you.
You're welcome.
Okay, we thank Professor Scartesini for his very important presentation.